Introduction to exhaust aftertreatment. Industry challenge. Technicians' objectives. Increased road calls, breakdown, and towing as a result of derates and shutdowns from emission failures. Disruption of delivery schedules. Technicians need to acquire necessary skills to service modern truck exhaust aftertreatment. Skills developed in electrical and diesel engine classes are leveraged to master the whys and hows of emission failure. How the system monitors temperatures and pressures. Why common after-treatment failures are increasing, and why testing and repair validation of key skills for effective diagnostic strategies. This is what it looks like on the dash. We have a flashing DPF lamp, diesel particulate filter. This is asking for a regen. We're going to get into the regen a little bit later on in here. How the government and the Environmental Protection Agency has moved over the years to improve air quality and to reduce emissions from motor vehicles. Caterpillar, early on, 1998, all the manufacturers on the right, all the major manufacturers, $84 million in fines. Caterpillar again with another $2.5 million. Volkswagen hit the jackpot here with their international diesel cheating scandal. $17 billion. Some of that money is filtering back to the states. Washington State Department of Transportation and Washington State Ferries are recipients of grants under the distribution of the $17 billion from the Environmental Protection Agency. Diesel exhaust produces harmful environmental outcomes: acid rain, photochemical smog, greenhouse effect, ozone depletion, and respiratory diseases. And it's a worldwide effort to improve the air quality by reducing emissions from automotive. Starts off in 1993. The legislation to improve the fuel by lowering the sulfur content. In 1994, it became law, and the sulfur is down to 15 parts per million. And the NOx emission has been reduced to a fraction in 2010 as to what was allowed back in the 1990s. Diesel exhaust pollutants: particulate matter, PM, soot, partially unburned hydrocarbon chains, unburnable elements of fuel and/or oil additives making their way into the cylinder. Oxides of nitrogen, NOx, normally separated. They combine during the combustion process to form nitric oxides and nitrogen dioxides. Emission sources of nitrogen oxides, NOx. 39% from road transportation, 18% from public electricity, and right there we have approximately 60% of our NOx is coming from public electricity, grid production, and road transportation. Exhaust pollutants in NOx. Subjected to high temperatures and pressures, they combine into nitrous oxide, 90%, nitrogen dioxide, nitrous oxide, and then collectively referred to as NOx. Here's the molecular structure. And here's what is known as the NOx PM dilemma. As temperatures rise, NOx will increase and particulate matter will decrease. When you cool the EGR and the combustion temperatures, the particulate matter will increase and the NOx will decrease. Lower combustion temperatures, more particulate matter and less NOx. And here's the sweet spot here, is 2,500 degrees in the combustion temperature. Here's a chart of how exhaust gas recirculation works. We're going to get into EGR now. The big feature here is the cooling with the EGR cooler, and it acts as a heat sink during combustion to reduce NOx. Here's a schematic of how NOx is controlled. The amount of NOx that's blended into the intake is controlled from ECM commands through the EGR valve. And here's the exhaust gas flow. It goes through the EGR cooler, and then it gets introduced into the intake side of the engine, combustion chamber. 800 to 1,000 degrees, the exhaust gas is lowered through the EGR cooler. The EGR valve increases and decreases the flow from the electronic control unit commands into the control valve, blending the correct amount of EGR into the intake stream. Introduction of EGR into cylinder lowers combustion temperatures, and lower combustion temperatures reduce NOx formation. EGR coolers, Cummins style, reduces combustion temperature, preventing the formation of NOx, oxides, and nitrogen pollutants. Temperature exhaust gas must be reduced before injected into the engine intake. EGR cooler can drop the temperature as much as 700 degrees Fahrenheit. Cooled EGR is controlled by the EGR valve in the intake air from the charged air cooler, then delivered to the intake manifold and the combustion chamber. This is the PACCAR version. It's considered a full flow cooler, that all the coolant in the engine will pass through the EGR cooler, making it very efficient in terms of a heat sink and for heat transfer. All coolant flows through the EGR cooler after leaving the block. The EGR cooler is the last component before the water pump. Reduces heat introduced to the engine side of the coolant. Here we have the Cummins version of the EGR valve on the ISX 15 liter. It sits on top of the EGR pipe after the EGR cooler. Exhaust gas from the EGR cooler to the EGR valve. And EGR valve smart device opens and closes to regulate the flow of EGR 12-volt DC pulse width modulated motor. It's a smart device on the can. On the cold side of the engine, we have a intake air from the charged air cooler coming in, and the intake air throttle has the EGR crossover pipe coming across from the hot side of the engine. Here we have the PACCAR EGR valve, which is can-based and a smart actuator. EGR Venturi, PACCAR version from 2010 and EPA 2013. It measures pressure differential delta P. The aftertreatment can, A can, calibrates the EGR flow in the PACCAR engines. Here's an example again of the EGR flow. Take a look at this again. You see that the gas is flowing from the exhaust manifold into the EGR cooler for heat transfer. The heat gets carried out, and the EGR gas is controlled and blended into the intake side of the engine to go into the combustion chamber, lowering combustion temperatures and producing dramatically less NOx. This is the diagram as it's shown. The introduction of the EGR into the cylinder lowers combustion temperature. Lower combustion temperatures reduces NOx formation. 2007 exhaust aftertreatment. The configuration was essentially EGR, exhaust gas recirculation, and the diesel oxidizing catalyst. Chemically converts carbon dioxide and hydrocarbons to CO2 and H2O. This portion of the canister is the diesel oxidizing catalyst. That's the front end. It's the first stop of the exhaust after the engine into the aftertreatment. It's the forward portion of this canister. Chemically, exhaust temperatures at 450 degrees are required for the chemically conversion to begin. It is needs approximately 480 to 500 to do what's called the passive regen. We'll get into that topic a little bit later. The outbound temperature will be in the neighborhood of 1100 degrees Fahrenheit. There's your exhaust flow. So the exhaust gas comes in. It is heated up in the oxidizing catalyst. It creates plenty of heat for the diesel particulate filter that will essentially burn the PM, the soot, into ash, and the ash will collect in the bottom of the diesel particulate filter. There's your exhaust flow. Inside the diesel oxidizing catalyst is a platinum wash coat, flow-through design, oxidation of hydrocarbons and carbon dioxide present in exhaust gas. And the hydrocarbons get converted into CO2 and water vapor. Carbon monoxide gets converted into CO2. And then they also, in 2007, we have the, again, the diesel particulate filter occurs after the DOC, and it has the pressure and temperature sensors on board here that allow it to burn off the hydrocarbons so that we have a PM is reduced to ash, and it collects in the bottom of the container. The system operates well at the 1,000 to 1,100 degree range, but it will shut down at 1,300 to prevent thermal damage to the components. This is another cutaway view of the diesel oxidizing catalyst and the diesel particulate filter, showing the exhaust flow. The DOC manages heat from base temperature of 482. Will go to 1,200 degrees during active and stationary regens. Diesel particulate filter in the center here, and then it traps soot and PM, reduces the particulate matter to ash during the regen process. And this is what the system looks like on the inside of the diesel particulate filter. Ceramic, has a wall flow filter. It's insulated and uninsulated, so it can deliver the heat to the particulate matter and burn it off into ash. So we have in 2010, we have a more enhanced system that includes selective catalytic reduction. And it was diesel exhaust aftertreatment with SCR. We're showing the diesel particulate filter and the DOC. We have a diffusion tube where we're injecting diesel exhaust fluid, DEF. It's injected and decomposes from diesel exhaust fluid into ammonia and enters the selective catalytic reduction can. NOx is reduced into water and nitrogen. This is a DEF control unit. Most locations are mounted on the chassis. Ambient temperatures from -40 to 40 to 85 degrees centigrade. Operation voltage 12 to 24 volts, 14 analog inputs from sensors and devices, 4 digital inputs, up to 15 outputs, and 2 CAN interfaces that has to go into the CAN engine and also into the J1939 CAN. Current draw after key off is very small, and at maximum heating and dosing is 28 amps. Connectors and pins are extremely sensitive to spreading and bending, so technicians are not to back probe this with pins. They have to use a breakout box. DEF dosing injector. Diesel exhaust fluid is 32.5% urea and 67.5% deionized water. This is a typical diesel exhaust fluid injector on the side of the diffusion tube. The urea is a compound of nitrogen. The DEF is subject to crystallization and freezing, so it has to be held at optimum temperature. Freezing and thawing of DEF will not degrade the product. DEF is clear, colorless liquid. DEF is stable, non-toxic solution, and it does not have any required hazard placars. This is a side view showing the cooler adaptation. The heatsink is made of aluminum. Coolant flows through here to keep the temperatures stable, and also air is injected to clear the line and the valve after it injects the diesel exhaust fluid. Then it gets a short blast of air to clean it out. DEF doser has 3 nozzles in this version. It's integrated 40 micron filter to keep the diesel exhaust fluid that's entering the nozzle to keep it clean. And it's coolant cooled. This is the DEF tank flow, showing the DEF tank from the DEF pump to back into the system. Coolant line thermostat value, coolant line to the tank, the DEF tank, the coolant return line, and we have the pump inlet, the pump, the return line, the injector line, which is going out to the diffusion tube, and the level sensor and temp sensor at the bottom of the DEF tank. A DEF quality sensor was added in 2016. And we have a standards here. This shows a 28-gallon tank with the blue cap on the side of the tractor. This one's on the driver's side. DEF consumption rate's about 2 to 3%. That's 2 to 3 gallons of DEF per 100 gallons of fuel. American Petroleum Institute API and ISO standards for the DEF manufacturing and content standards have to be very specific to work correctly. This is the basic rack view of the diesel oxidizing catalyst, diesel particulate filter, diesel exhaust fluid injector, the decomposition tube between the two cans, and we have the SCR, selective catalytic reduction chamber. This is what happens inside of selective catalytic reduction. We have ammonia coming in because the DEF is decomposing into ammonia, NH3. It has 3 hydrogen molecules, and the NOx comes in the exhaust stream through the decomposition tube. It goes through the catalyst, which has the precious metals in the honeycomb, and it is converted into, chemically transformed into water vapor and nitrogen. The ammonia coats the SCR catalyst and binds with the NOx as they pass over the catalyst. Once bound, the NOx will create a chemical reaction with the 3 NH3 and ammonia, resulting in nitrogen and water. This is a side view of the selective catalytic reduction can. The can will have 2 bricks made of a SCR layer, and the NOx will come in, the ammonia will come in, coat the SCR layer, and then it will be chemically transposed into nitrogen and into water. And it breaks down the dangerous NOx into harmless nitrogen water. So this is basically what it does inside. Okay, this is a overall view of the air handling, the intake turbo cooled via charged air cooler line. So the intake air is cooled normally through the charged air cooler. That's in the front of the radiator. The exhaust is cooled via EGR cooler. It's an air to coolant heat transfer. It can drop as much as 700 degrees from the exhaust temperature. The EGR valve controls the mix of cooled intake and cooled exhaust gases into the intake side of the engine. That's the upbound NOx sensor. So we have a NOx sensor that is, and this iteration shows it between the turbo and the DOC. It's the first stop, so there's going to be both a temperature and a NOx sensor upstream of the diesel oxidizing catalyst. Okay, DEF injection will be managed via controls from the ACAN, aftertreatment can, to regulate the timing and the rate of DEF flow, and that is based on sensing the inbound NOx, how much NOx is coming into the system, and how much NOx is leaving the system, and that is calibrates and commands the diesel exhaust fluid injection into the diffusion chamber. There's our DEF injector. Okay, after treatment fuel injector, hydrocarbons. We need to add fuel into the exhaust in order to build temperature for our active and stationary regens. And this is done through a variety of calculations, and we'll put a light up on the dash that the driver has to conform to a regen. This is what it looks like on the Cummins 15-liter CM2250. Here we have a hydrocarbon diesel fuel injector, and here we have the NOx sensor. The turbo's on this side, and this pipe plumbing leads out to the diesel oxidizing catalyst. There's your fuel line, coolant lines for the fuel injection, hydrocarbon injector body, coolant line out, upstream knock sensor, and exhaust from the turbo to the rear of the engine. This is another view of the hydrocarbon injection that is going to put fuel into the exhaust stream and will build heat to the correct temperatures necessary for the start of the after-treatment process. There's our doser. It's putting fuel into the exhaust stream. Regeneration systems. The truck has to periodically go into what's called a regeneration. When soot levels exceed 100%, the RS light illuminates. 125%, it blinks. The engine begins to derate at 150% to 25% power. 175% soot level, the engine derates 75%, and at 200%, the engine will shut down. Three types of regens. Passive regen, no fuel is added. There's enough residual heat from the exhaust to support the process, and it will the DOC will produce enough heat to cook the particulate matter into the soot into ash. Active regen, fuel is added, and it initiates by an after-treatment command, and it's going to go through the A can, the after-treatment can, and it's going to have speed, load, and coolant temperature as part of the active regen. This is when the truck is running. Stationary regen, fuel is also added, but the truck needs to be parked in a safe location, and the driver can initiate that through the dash switch. The controller area network, we have the engine control unit, the after-treatment control module. They are commanding the EGR valve to select the best mix of EGR gases into the intake, and have the hydrocarbon doser, which will be putting the best amount of fuel in as necessary to build heat into the diesel oxidizing catalyst. And also it's going to command the depth dosing injector to make sure that we are putting enough ammonia into the selective catalytic reduction from the diffusion of the urea into ammonia, so that we are correcting the amount of NOx that is introduced into the system. There's many calculations going on here to make this work correctly. Okay, this is another view of how the ammonia sensors, the DPF temperatures, and the engine and the terminating resistors are laid out in after-treatment ECU, and there's a variety of temperatures and pressures that are collected throughout the system to determine the next best action in ECM and ACAN commands. Here again we have the after-treatment dash lamp. So here we're looking at it's time to do a regen. That's what the flashing light is meaning. Okay, we have single canister diesel exhaust after-treatment from 2010 to present. This has been a big improvement. After-treatment is becoming less of a fail point. Trucks that do over-the-road runs are experiencing much greater improvement in fewer regens and less problems with the after-treatment. They're compact and lighter. They're improved thermal efficiency. The Detroit version of this does have 2 DPFs in it, so it has 2 diesel particulate filters that allows it to collect more ash and have greater lifespan. Enhanced serviceability.